Good evening, students. So, in our previous session, we are in the journey of chemical bonding. In the previous session, we were thoroughly discussing about polarization, the phenomenon of migration or dislocation, delocalization of negative charge from the anion, usually the bigger one, towards a cation which is nearby placed, such that the bond type slowly moves towards covalent bond. Polarization is a phenomenon that leads to covalent bond. We have thoroughly had a discussion on this. Especially the cations are obtained, of course, by loss of electrons from neutral atoms. Once electrons are lost from an atom, the effective nuclear charge will increase. And if the effective nuclear charge increases and electron deficiency is also there in the cation, it prefers to attract the electron density from the nearby anion, wherein the anion's Z effective will be less. Because how an anion is obtained? By adding electrons to a neutral atom. So extra electrons would come and join. The more and more electrons is added to an atom, the effective nuclear charge will gradually decrease. So the nucleus does not have much hold on the valence electrons, whatever electron density, electron cloud, whatever you say, will not be able to hold the density. And generally, we always say ionic bond is non-directional only because the ions are spherical, perfectly spherical. Or you can say the charge is spherically distributed on each ion. So the spherically distributed charge on each ion will make the bond non-directional, because in any direction the ion can come. But once this kind of polarization occurs, the spherical symmetry of the anion is lost. The symmetry is lost because some of the electron density will drift towards the cation, and that spherical symmetry will be lost. So some of the electron charge will be accumulated in between cation and anion. That makes a lot of difference in chemistry, as we already had a thorough discussion on this. Basically, the cation is spherical, we expect. Cation is spherical, we expect. The anion to be spherical, we expect. But the nucleus Z effective becoming more, because this is positive ion and this is negative ion. This nucleus will have low Z effective. There occurs a deformation in the anion and the electron density will drift towards this, which leads to accumulation of charge between cation and anion, and this is almost like a result kind of a thing from sharing of electrons, and this leads to covalent nature. Had the ions been perfectly spherical, there will be, and non-directional attraction is there, that will be ionic in nature. But some charge density distributes in between the nuclei, obviously there will be some covalent nature developed. So this is what we were discussing on the other day. What could be the applications of this polarization? The first and foremost application is, first of all, the polarization leads to covalent nature. Because we are in chemical bonding, we are highlighting that particular point. There we had Fajan's rules also thoroughly discussed, that small cation, high charged cation, we already had a discussion, but I am just reminding, high charged cation and the pseudo inert gas cation, or you can say D block cations, because the nucleus is more exposed, and these cations are highly polarizing, high polarizing power. They have high polarizing power. So they try to drift the electron density from the nearby anions. Similarly, if you can think of anions, what happens? Large anions, because large anion means nucleus will be very much buried inside. So that large anion and high charged anion. What do you mean by high charged anion? You have added more electrons to the anion. High charged anions will have highly polarizable. So it's large anion is not a good condition for ionic bond. Similarly, high charged anion is also not good. In a way, high charged cation and high charged anion both are not good for ionic bond formation. So what will happen? High charged cation and high charged anion are kept together. Definitely polarization takes place. Once polarization occurs, the bond becomes more covalent in nature. So for ionic character, there should be less charge. A big cation is preferred, because small cation again leads to polarization. Large anion leads to polarization. This is a very good combination for a covalent character, but not for ionic character. So this particular usual thought process should be always habituated, to every student. Every student should get habituated to this kind of a phenomenon, because at many places we use this polarization phenomenon to conclude many things. So here I would like to show you different environments so that you will have some more idea on which is more covalent, which is more ionic, based on just Fajan's rules, all these things. So we'll see different chemical environments and try to conclude certain things with simple examples, so that we'll get a good practice on looking at a molecule in polarization sense. So this is very essential. So we'll think of it now. Just we'll take some question kind of a things and try to analyze them. See, he gave four entities: lithium chloride, beryllium chloride, boron chloride, and carbon chloride. See, by seeing this, he is just asking covalent bond character order. So lithium, beryllium, boron, carbon. All the four belong to one period. You are moving from left to right. Of course, as we all know that atomic size gradually decreases as you move from left to right. So lithium, beryllium, boron, carbon. Now you can assign some charges. See, lithium chloride has got lithium plus, beryllium chloride has got beryllium plus 2, assuming it's ionic, and boron chloride, if you try to assign some charge to boron, you can give plus 3. If you want to assign some charge to carbon, you can give plus 4. So now what is happening? There is plus, plus 2, plus 3 and plus 4. And the charge, already the atomic size itself decreases. As more and more electrons you have removed, the size will still shrink very effectively. Very much the size will shrink. Carbon plus 4 is the smallest entity, smallest ion with highest positive charge. And as we have earlier discussed that a cation with less size and high charge will have highest polarizing power. So who can pull the electron density from chloride ion to a very great extent? This carbon plus 4 can pull. So carbon plus 4 pulls the electron density from chloride, and you are going to have a covalent bond here. So the best covalent. And so in this particular row, what you can conclude, CCl4 is the best covalent compound, second best is BCl3, and then comes BeCl2, then comes lithium chloride. So as the size decreases from lithium to carbon, as the charge increases, polarizing power increases, As the polarizing power increases, covalent character increases. So in the given list, the best covalent compound is CCl4 is the best covalent compound. Second best is BCl3, then this. So to some extent, the best ionic compound is lithium chloride, even though it is originally not much ionic, but in this particular list, relatively when you speak, it is the most ionic. CCl4 is the most covalent. Of course, the answer could be second. So here what I would like to suggest, the more the charge on the cation, the more its polarizing power. In that sense, if you speak, most of the conclusions you can make easy. CCl4 actually is a covalent compound because carbon is a non-metal, chlorine is also a non-metal. But in the sense of polarization, you can always feel like this. C plus 4 can really pull the electron density from chloride to a very great extent, making the bond covalent. The correct order of decreasing polarizability. See, this is not polarizing power. They're speaking about polarizability. What do you mean by polarizability? How good an anion can be polarized? Just now I told you, a large anion can be easily polarized because in a large anion, the nucleus will be very much buried inside. There will be many electrons outside. Nucleus is buried very much inside. This will have no charge, no control on the outer electrons. So you can easily pull the electron density from such a anion. So if there is a large anion, it is easily polarizable. High charged anion is easily polarizable. English sake, I am speaking so much. If the anion is large, you can easily polarize it. Charge is more, you can easily polarize it. So let us now think of it. So you have got which ions given? Fluoride, chloride, bromide, iodide. Beyond any doubt, iodide is the best and biggest ion. So fluoride is the smallest anion, chloride, bromide, iodide. So it is very easy to polarize lithium. Iodide. You keep some metal cation here, which electron density can be easily grabbed by this M plus X. Fluoride, it's very difficult to pull the electron density. Iodide density can be pulled. So this will give a better covalent compound. This will give better ionic compound. So what is the best order? Fluoride, chloride, iodide, bromide, chloride, fluoride is the order in which the polarizability decreases. See, again a simple ion is given. These are all just warm-up exercise kind of a thing. Students should get casually used to speak all this polarizing because in future we make many conclusions based on this. Magnesium ion is given, aluminum ion is given, calcium ion is given, sodium ion is given. Which has highest polarizing power? See, to decide this, you must have complete idea on the periodic table. Right from the beginning, I have been advising the students to have good hold on the periodic table. By seeing element symbols and all, you must be able to identify to which particular group or to which particular period a particular ion or atom belongs to. See, magnesium is a second group, second A, calcium is second A, sodium is first A, aluminum is third A. So as you are moving from left to right, you are coming across this, two belong to second A. So where do you find them? So magnesium, below magnesium you will have calcium, next to magnesium you will have aluminum, left to magnesium you will have sodium. So that is the beauty of it. Sodium plus alkali metal, magnesium 2 plus alkali earth metal, aluminum 3 plus boron family metal, calcium 2 plus alkali earth metal. These are given. So he is asking which has got highest polarizing power, which can one with very less size and more charge. So whose size is less? As you move from sodium to magnesium to aluminum, in the atoms itself, atomic size itself, there is a decrease. And you have after all removed only one electron from sodium, this is smaller. And you have removed 2 electrons from magnesium, it will become still smaller. You have removed 3 electrons from aluminum, it is still very micro smaller. And obviously when you come down in the group from magnesium to calcium, the size increases. So now we are searching for a small ion with highest charge. Excuse me. So among the given 4 ions, aluminum charge is highest. Aluminum is the smallest. So it will have highest polarizing power. So what do you understand? Suppose I keep sodium plus, I keep magnesium plus 2, I keep aluminum 3 plus, and I keep calcium 2 plus. If I keep any some ion here, some oxide ion. So who can pull the electron density from oxide ion? Very easily and to a great extent. Obviously, aluminum plus 3 will pull the electron density out from oxide very much, because it's the smallest cation with highest charge. So this is how we'll have to analyze the things. So suppose sodium oxide, magnesium oxide, calcium oxide, aluminum oxide, which will be the most covalent oxide. So obviously, because here the polarization is more, aluminum oxide will be least ionic and most covalent. Which will be the most ionic? Where the polarization is less, that will be the most ionic. Sodium oxide will be most ionic among them. Most ionic. Least ionic or most covalent is Al2O3. So coming to my next question, the correct order of increasing covalent character. Almost it is the first question like, but zigzag. Sodium chloride, lithium chloride, beryllium chloride. See, somewhat top to bottom, somewhat left to right. So you must know lithium and sodium belong to first group, and who is the other thing? Beryllium chloride. Beryllium chloride is second group. And you are going from left to right and top to bottom also. So as you move from top to bottom, metal ion size will increase, polarizing power will decrease. So this will be more ionic than lithium chloride. As you move from left to right, metal ion size will decrease, so polarizing power will increase. Beryllium chloride will be more covalent. So sodium chloride is most ionic, beryllium chloride is more covalent, lithium chloride is in the middle. So what can we conclude? See, lithium plus is somewhat larger than beryllium plus 2 is very small. So it will have highest polarizing power. So it leads to covalent nature of beryllium chloride. Compared to lithium chloride, beryllium chloride is a better covalent compound. So lithium chloride to sodium chloride, ionic size increases, polarizing power decreases. Therefore, ionic character will increase, covalent character will decrease. So best ionic compound, lithium chloride, sodium chloride. So sodium chloride, then comes lithium chloride, then comes beryllium chloride in covalent character. That's really good. And coming to the next question, it is now anions changed. The pair with more ionic nature and less melting point. See, what do you mean by this melting point? Ionic nature should be more, melting point should be less. He wants to identify two compounds, least melting point compound and high ionic nature compound you have to find. First of all, we need to think of again ionic character, covalent character also, and at the same time how to decide the ionic nature. See, here I would like to advise you something very, very important. Ionic bond strength is different. Ionic bond strength is different. Ionic bond nature is different. Ionic nature is different. Ionic nature means how good an ionic compound it is. And proved that it is ionic compound, what is the bond strength? How good the cation and anion attract each other. And we are pretty sure, I can give you one beautiful example. If you take cesium fluoride, cesium plus, fluoride minus. Cesium is a very big ion, fluoride is a very small ion. So there can never be polarization taking place here, because a small anion will not let the charge move out. A big cation will not attract the charge at all. So there can never be polarization occurring the charges will be static and the force of attraction will be more electrostatic in nature. Electrostatic in nature. So this is a very good ionic compound. But what about the attraction between these two ions? The attraction between these two will be very less because this is such a big cation, this is such a small anion. The distance between the nuclei will be too far, too big. So if you want to know the force of attraction between two opposite charges, force of attraction between two opposite charges is directly proportional to charge 1, charge 2 by the distance between charge square according to Coulomb's inverse square law. So if you want to compare lithium fluoride and cesium fluoride, what comments can we make? Lithium fluoride is a very good ionic compound because electronegativity difference is too much. Fluorine is 4.0, lithium is approximately 1.0. Since there is a good electronegativity difference between lithium and fluorine, you can definitely say this is ionic. At the same time, this is also ionic. This is a very good ionic compound because cesium plus is there, fluoride minus is there. A big cation and a small anion, almost you can rule out polarization. If polarization is not there, it will be more ionic in nature, nature-wise. But what about this force I am speaking about? See, lithium plus is a small cation, fluoride is a small anion. So obviously, the force, the distance between lithium plus and fluoride minus will be very less. If the less the distance between the two ions, force of attraction will be more. More the distance between the ions, force of attraction will be less. So when it comes to ionic strength, think of the radius of cation and radius of anion. So force of attraction between two ions. That ionic bond strength depends on the size. Smaller the size of ions, greater the bond strength. Whereas nature-wise, if you think, big cation and small anion will give more ionic nature because polarization is minimized. So be careful in the questions. Here he is asking ionic nature, more ionic nature. So for more ionic nature, cation should be large, anion should be small, and both should have very low charges. Unfortunately or fortunately, all the pairs of compounds are given with lithium only. So no need to break our head to decide which is most ionic. Obviously, fluorine being most electronegative, lithium fluoride will have highest ionic character. But what about less melting point? Melting point generally depends on lattice energy. You have to break the lattice. See, as I told you, in many compounds, ions are distributed in different lattices. Anyhow, time has come. I would like to spend some time on the lattice structures also. We'll spend some time. Anyhow, we have got some interesting phenomenon about melting point and all. I'll discuss some lattice aspects also. So now, to break this lattice, if the attractions are poor, the lattice can be broken easily. So lithium plus and iodide, you have got iodide being very big, the attraction is less, the lattice can be easily broken. So it will have less melting point. So lithium fluoride and lithium iodide is the example for the question. Coming to, just now I spoke to you, what do you mean by lattice? All ionic compounds will crystallize in perfect lattices, crystal lattices. And we have got so many varieties of three-dimensional structures of solids. Crystalline solids get crystallized in different varieties of lattices. We have got around 14 varieties of unit cells. 14 varieties of unit cells we have got. Of course, in them, there is some word which you use, unit cell. It is like a brick in the wall. Unit cell is the smallest part in a crystal, which can describe the entire crystal. A crystal is made up of so many unit cells, which you are going to learn in higher classes, maybe in 12th in solid state chemistry. Right now, every ionic crystal adopts one particular variety of crystal structure, in which unit cell is the minimum unit which describes the entire structure of the crystal. So one should clearly understand unit cell so that you can completely understand the crystal. Suppose if you take sodium chloride crystal, unit cell will be like this. This is called unit cell, where you can have a cubic repeating unit. As I told you, unit cell is always a repeating unit. So this repeats in all the directions, top and bottom, left and right, front and back, like. So this is a cubical unit cell. In this, chloride ions occupy the corners. Chloride ions occupy the corners. And now the time has come. So top face, bottom face, left face, right face, back face and front face. All faces are also occupied by, what should I say, chloride ions. Whatever I put like this, that's a chloride ion. And where will sodium ions occupy in this particular arrangement? Chlorides make a lattice, sodium ions will embed themselves in that particular lattice. So edges are free. At the edge center you will have sodium. At the center of the edge you can have sodium. This is sodium, this is also sodium, sodium, sodium. See, every edge is occupied by sodium. Dear students, I always tell you only one thing. This is not the entire crystal. This is only one smallest part of the crystal. Means what? This keeps on repeating in many, in all directions. Even at the center you will have a sodium. This orange dot represents sodium ion. See how beautifully the ions are arranged in the crystal. They attract each other with tremendous attraction, and that attraction results in the release of energy. That energy is called the lattice energy. And I repeatedly tell you only one thing. This is only a unit cell. What do you mean by unit cell? The smallest part of the crystal, which can explain the entire crystal. It keeps on repeating in all the directions. There is a very logical and wonderful calculation what you can do in this particular regarding this unit cell or about the crystal and all. Suppose someone will ask you, one chloride is surrounded by how many sodiums? One chloride is surrounded by how many sodiums? That is the question. That's a very funny, interesting question, logical. So immediately check for the chloride and check how many sodiums are around it. Now let us just think of that wonderful question. How many chlorides or how many sodiums are present around each chloride? As I told you, that circle is a chloride. In this particular cube, on the top face you see one circle. That circle is chloride. How many sodiums are the nearest neighbors of that chloride? See this sodium, left side sodium, see right edge sodium, back edge sodium, front edge sodium. See how many sodiums are you seeing? Nearest neighbors 4 in that particular layer, and that is not enough. In the down also, at the body center position there is a sodium. You have seen one sodium there. So it is a sodium. And above this also you will find a sodium. Above the, where is this sodium? This sodium is present in the next cube. So one chloride is surrounded by how many sodiums? 6 sodiums. Cl minus, coordination number we call it 6. Coordination number means nearest neighbors. So one sodium is surrounded by how many chlorides? My next question. See, chloride's coordination number is 6. Means what? Chloride is surrounded by 6 sodiums. One sodium is surrounded by how many nearest neighboring chlorides? Now we will select one sodium and check. I will select one body centered sodium. See, in the body sodium, if I select, how many chlorides are there? See, go back, go front. You are seeing 2 chlorides. Go left, go right. 2 chlorides. Go top, go bottom. So totally how many chlorides are around sodium? 6. So sodium plus coordination number is also 6. See, such most beautiful questions we can always analyze in this particular three-dimensional lattice of crystal structures. But don't think all crystals will adopt the same kind of a structure. It all depends on the size of cation, size of anion and all. Now let me draw this again and we'll work out some interesting things. Suppose I have got this unit cell. Is this unit cell only one unit cell present in the entire crystal? No. the crystal, entire sodium chloride. Suppose you have got a dish. In that dish you have got so much of sodium chloride, some powder, sodium chloride powder, crystals are there. In this crystal you will have so many unit cells. This is only one unit cell what we have drawn here. And if you remember well, I said every corner is occupied by a chloride. So this is a very interesting aspect. So chlorides, every corner has a chloride. Top, bottom, left, right, back and front. So you have got all chlorides, just now I told. And where do you have sodiums? At the middle of the cube, and every edge has got a sodium. See the beauty of the structure we have already drawn. Now my question is, in one unit cell how many sodiums and how many chlorides are there? So don't physically count, because there is a simple logic, because there is a very easy logic. Like suppose you have got one unit cell like this. It's a small unit cell of the crystal, but this is not the entire crystal. It continues like this to the next place. So suppose you have got one ion at the body center position. That ion totally belongs to one unit cell. But if you have any ion on the face of it, that face ion, you should not take it as one. You have to take it as only half. Why? This is shared by two unit cells. Similarly, if you have any edge center atom, on the center of an edge, you have to count only 1/4. You have to count only 1/4, because that edge is common for 4 unit cells. How 4? The 1, 2, and below there will be again 2, no? Like this. If you take an edge, see here, edge is there. That edge is common for 4 unit cells. You have to count only 1/4. Similarly, if you take a corner is 1/8. Corner is only 1/8. So let me just tell you one thing. If at all you have a body ion, you have to count 1. You have to count it as 1. If you have a phase ion, you have to count it as only half. If you have an edge ion, you have to count it as 1/4. If you have a corner ion, you have to count it as 1/8. Let me tell, 1 for body, half for phase ion, 1/4 for edge ion, 1/8 only for corner ion. Like that you have to count. Now let us count how many sodiums and how many chlorides are there in this unit cell. Where are you seeing chlorides? Corners. Corner means how much should you count? Corner means 1/8. How many corners are there? 8 corners. 8 corners. So 8 into 1/8 will make 1 chloride. And on each face you have 1 chlorine. So how many faces are there? Left face, right face, back face, front face, top face, bottom face. Totally 6 faces. 6 into 1/2, because face is 1/2. So that means that gives 3. So totally there are 4 chlorides in this unit cell. 4 chlorides. So don't physically count and decide. Don't say 14 chlorides. There are only effectively 4 chlorides. How many sodiums are there? At the body there is 1 sodium. So 1 into 1, 1. At each edge you have got 1 sodium. There are 12 edges. So 12 into 1/4 will give me 3. So totally 4. So there are totally 4 sodiums, 4 chlorides. 1 sodium chloride unit cell consists of 4 sodiums and 4 chlorides. That's the beauty of the analysis of crystal lattices. Suppose if some of the ion is a very small ion, what will that do? That will start attracting, that will start polarizing the nearby anions. And the lattice will become what? Covalent lattice. Slowly. If at all the ions are very small and anion is very big, what would happen? This crystal will gradually, while crystallizing, polarization will take place and the crystal will show covalent properties. We can call it a covalent compound. So this is quite common in chemistry. Suppose zinc sulfide is there. Zinc is very small. Sulfide is very big. So obviously zinc will polarize sulfide and make the ionic crystal a covalent one. So this is all in the game. So dear students, so the beauty of sodium chloride, what did you learn? One sodium chloride unit cell effectively possesses 4 sodium ions and 4 chloride ions. If someone will ask you what is the mass of a unit cell, you can easily tell 4 into 23 plus 4 into 35.5. So it gives you somewhere around 234 AMU. 234 AMU is the mass of one unit cell of sodium chloride. There will be 4 sodiums, 4 chlorides. See, many things like this we can actually work out with ionic crystals and all. In those crystals also polarization, due to polarization, the nature of the crystal gradually may become covalent. Suppose you take cesium chloride, cesium being very big, chloride being very small, even though formula wise it looks like sodium chloride, it adopts a different kind of structure because cesium is too big compared to sodium. So cesium chloride will have at the body center position cesium. Cesium will be at the body center and all chlorides will occupy the corners. That's it. This structure is very simple. This is called body centered cubic. Each cesium is surrounded by 8 chlorides. Each chloride is surrounded by 8 cesiums. So though a bit deviation from the present topic, I just wanted to share these things because there is a word melting point has come in this question. I felt like sharing you the crystal structures of few chemicals so that to understand what do you mean by melting point. If you keep on raising the temperature of a crystal, the lattice will break down into molten ions. So that is called melting point. So if the strong bonds are there in the lattice, the melting point will be high. Which of the following is more ionic again? Ionic means what? He is asking ionic. We don't want polarization to take place. We don't want polarization to take place. See, every question I am trying to analyze by means of polarization only. In those terms, I want you to learn. So, polarization should be least. I don't want more polarization to take place. So, we have to compare anions and cations. Luckily, all are anions common, all are chlorides. So, you need to bother about cation only. Sodium plus, magnesium 2 plus, potassium plus and calcium 2 plus. Always remember, second group cations are more polarizing in nature than first group cations because first group cations possess less charge. First group cations are large in size. First group cations are less charge and size wise they are large compared to second group cations. So second group cations polarize more, means they form towards a bit covalent nature. First group cations are less polarizing in nature, so they are more towards ionic in nature. Now sodium and potassium are left. In these two, potassium is larger. Large cations cannot polarize well. It should become a habit for all of you. So potassium cannot polarize well means we don't want polarization because we want ionic compound. So potassium chloride is the best ionic compound in the given 4 compounds. Now at the same time, can we identify which is the least ionic among these 4? Very simple. Least ionic we want. So magnesium has got high charge and less size. The charge is more, size is less. So it is most polarizing. So least ionic. So dear students, this will be more covalent in nature than ionic comparatively. So this is now about anions. In this particular question, he fixed the cation. So boron, 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 boron. In all the 4 cases, boron only. The anion case, it changed. I minus, Cl minus, F minus, Br minus. They belong to halogen group: fluorine, chlorine, bromine, iodine. You all pretty well know what is the size of anions: fluoride, chloride, bromide, iodide. And as the size of anion increases, that polarizability increases. Polarization leads to covalent character. So Bi3 will be most covalent in nature. Anion is large, covalent in nature. Almost, yeah. In this question, both cations and anions are changed. You have to be careful. Cations are changed, anions are also changed. So sodium is one cation, first group, and in first group you don't have anything. Then magnesium, second group cation. Aluminium, third group cation is also given. Okay, first let us analyze the cations. Among sodium, magnesium and aluminium, as I told you many times, sodium to magnesium to aluminium, atomic size itself will decrease. Aluminium being more charged cation, the charge will still shrink down. So this is the least sized ion. Aluminium 3 plus is least sized ion. So it will have powerful polarizing capacity. Now, so we have got 2 aluminium, these things. He wants more covalent character. So we have ignored magnesium and sodium. We are going for aluminium. Among aluminium, we have got again 2. One with chloride, one with iodide. Al3 plus, Al3 plus. This is chloride, this is iodide. Now which will be easily polarized? Iodide being a larger anion will be easily polarized. So obviously this bond will be more covalent in nature. Highest covalent character is found in which of the following? Very simple question, I think repeated. Calcium, calcium, calcium. Instead of boron, this time he put a metal. And the other anion is fluoride, chloride, iodide, bromide. As we all know, bigger ions are easily polarized. This is highly polarized. Calcium iodide is most covalent. I advise students to be careful among the groups fluoride, chloride, bromide, iodide. One must know as 7th group. Oxide, sulfide, selenide, telluride. Like this. Very rare telluride anyhow. So on the left side you have nitride. Then you may have carbide. Powerful, very much polarizable. You know, nitride, phosphide, highly polarizable because size is more, charge is more. These are all polarizable anions. Among them, least polarizable anion is fluoride because the electron density is tightly packed, and remaining all well polarized. Depending on the cation, extent of polarization will be decided. Suppose you have these two, phosphide is more polarizable. You have these two, carbide is more polarizable because -4, very difficult for the nucleus to hold. Oxide and sulfide is more polarizable. Suppose you have got silver oxide and silver sulfide. Both silvers are highly polarizing in nature, but oxide and sulfide is more polarizable. So this will be more covalent in nature. So like this we'll have to analyze. Similarly, you can always make second group cation more polarizing in nature than first group cations. Aluminium is still more polarizing and all. At the same time, if the in transition elements one more advantage or disadvantage is there, there will be variable oxidation states. You have iron plus 2, iron plus 3, Mn plus 2, Mn plus 4, Mn plus 3 is there, Mn plus 4 like. Suppose when this positive charge increases, the size keeps on decreasing, the nuclear power keeps on increasing, the ion will become more polarizing in nature. Suppose you have got MnCl2, MnCl3, MnCl4, which will be most covalent. MnCl4 will be the most covalent in nature. So it will be almost like this, dear students, and keep enjoying this kind of logic. So this is a very, very peculiar question. Which one is most ionic? Most ionic. There can be 100 varieties of directions we can think. See, phosphorus and oxygen, both are non-metals. Both are non-metals. So I would like to advise you something. As the positive charge on an atom increases, gradually its non-metallic character will increase. Because suppose you have got phosphorus with +3 charge and phosphorus with +5 charge, this will become more electronegative. Because it is becoming deficient, it will try to pull the electron density more towards it, will become more electronegative. High charged ions, whether it will be metal ion or non-metal ion, will tend to give you more covalent character. So as I told you, ferrous chloride is less covalent, ferric chloride is more covalent in nature. As the charge of ion increases, covalent nature increases. Charge of cation. See, phosphorus pentoxide. Luckily both are non-metals. Definitely it will be a covalent molecule. Here there is a problem. Chromium is there, manganese is there, manganese is there. This chromium is now attached with 3 oxygens. So chromium oxide means -6 contribution from oxygens. So this chromium is in what state? Extremely positive state, highest state. Chromium belongs to 6th group. It has got +6 oxidation state. Means what? Chromium is in its highest oxidation state. So it will be tremendously polarizing in nature. Highest oxidation state. Powerful polarizer. It will almost pull the electron density from oxygen, 3 oxygens, and you are going to get which nature? Covalent nature. And coming to 2 manganese oxides, in here if you count, manganese will have +7, Mn2O7. Mn2O7 means what? Manganese is in +7 state, because each oxygen is -2. There are 7 oxygens, -14. There are 2 manganese atoms, so +14. Each manganese is in +7 state. +7 is a very big positive charge, so manganese will have tremendous polarizing power. It will polarize the oxygens, oxide ions, so it will be covalent in nature. This manganese is just +2. +2 manganese cannot polarize as good as +7 manganese, and like +6 chromium. And of course this is +5 phosphorus, and anyhow both are non-metals. So I think this is the best ionic compound, MnO. Low oxidation state on manganese, less polarizing. Less the polarization, more the ionic nature. A good question. This is about hydrolysis, which you should learn in the next class. This is a very good question. See, the following compounds are in order of increasing thermal stabilities. Here I would like to tell something. Suppose you have got a carbonate ion. There is an ionic compound. Some metal is there, +X. There is a carbonate ion. Carbonate is a oxo ion. We call it an oxo ion. Oxo ion means what? There will be a non-metal or a metal attached to some oxygens with negative charge or positive charge. Positive oxo ions are also there, negative oxo ions. Now they undergo a kind of phenomenon called resonance, which you will learn later. This electron gets delocalized and it will be stable. Suppose this cation polarizes the electron density from these oxides. What will happen? This gets destabilized. Destabilized means it will lose its stability if this polarization takes place. If the cation in a salt polarizes in the crystal, that's what I was telling. Sometimes in the crystal lattice, what would happen? suppose you have got some carbonate here, CO3 minus 2 here, and you have got some metal here. What may happen? This metal will try to polarize this carbonate ion. Because of the pulling of the electron density, this carbonate will get destabilized. So once this is get destabilized, if you heat this lattice, easily this will release carbon dioxide. So here what you should understand, suppose I heat beryllium carbonate, I will be getting beryllium oxide and carbon dioxide. If I heat, let me say barium carbonate, if I heat, I will get barium oxide and carbon dioxide. But this is very difficult. Second one is difficult. First one is difficult, I mean to say. Why this is more stable? The reason is the ionic strength is more. More ionic in nature. See, barium being a very big ion will not go to the carbonate ions for polarization. No polarization. If there is no polarization, the charge will be stabilized on carbonate and there will be resonance taking place, and this is stable. If this charge is stolen by somebody, this will be getting destabilized, and you can, on heating, that will release carbon dioxide. So whenever an oxo ion like carbonate is surrounded by some ions like this, which are highly polarizing, this will get destabilized and will give carbon dioxide out. If this does not polarize, the carbonate will be stable, so you will not get carbon dioxide on heat. You take potassium carbonate and heat. Nothing will happen, no reaction. Because potassium will not polarize carbonate. Whereas you take lithium carbonate and heat, definitely lithium will polarize carbonate and you are going to get lithium oxide and carbon dioxide. That is the beauty. Somebody asks, lithium carbonate on heating gives carbon dioxide, potassium carbonate on heating gives nothing. No reaction. Why? What answer will you give? Hate it, blame it on polarization. Lithium plus is a very small ion, so it will polarize carbonate. Once it polarizes carbonate will become destabilized and you can easily get carbon dioxide out. Similarly, if you have sodium bicarbonate, see the beauty of it. If you heat sodium carbonate at a very high temperature also, no reaction. Heat it strongly, nothing will happen. It will get heated up, that's all. Whereas if you heat sodium bicarbonate somewhere around 200, 300, you are going to get carbon dioxide released. What is the difference? In sodium carbonate ion is having sodium ions nearby it, which never polarize because of their big size. They don't polarize carbonate ion. Whereas in sodium bicarbonate, there is one hydrogen and one sodium, a powerful polarizer. This is a very powerful polarizing cation. So due to its polarization, this bond becomes weak. So carbon dioxide can come out easily. So bicarbonates on heating liberate carbon dioxide. Carbonates of first year group do not give carbon dioxide. All these you can blame the polarization phenomenon. So in this particular question, what is he asking? See, he gave potassium carbonate and he gave magnesium carbonate and he gave calcium carbonate and beryllium carbonate. See the nice combination of carbonates. He is asking which is thermally most stable, which is thermally least stable. What do you mean by thermal stability? So if you heat them, who can lose carbon dioxide easily, who cannot lose carbon dioxide easily? That is the $1 million question. Just now I told you, this is first group, this is second group. He took one first group cation and 3 second group cations. Let us put them in that. Potassium first group, second group beryllium, magnesium, calcium he gave. Beryllium 2+, magnesium 2+, calcium 2+, fixed oxidation states. And we know pretty well, first group cations are very large in size, charge is less, so they don't polarize carbonate. So carbonate is safe. Carbonate is safe. Whereas second group cations have small size and their charge is more. The charge is more, they polarize better. So now we have a dilemma. In these four, who can polarize more? The size of cation is small, that can polarize more. Next best, then next comes. So polarization order, beryllium 2 plus polarizes better than magnesium 2 plus, better than calcium 2 plus. Now, this will not polarize. What was the question? Thermal stability order. So if you keep beryllium carbonate, you can easily decompose this. Why? Beryllium 2 plus will cause the damage to carbonate, and upon heating it will easily liberate carbon dioxide. Very easily it will liberate carbon dioxide. But magnesium being larger than beryllium, it cannot polarize carbonate easily. Similarly, calcium being still larger, this also cannot polarize carbonate. So the extent of polarization decreases as you go down, so the stability of the carbonate will increase. Polarization leads to less stability. So there is no polarization. This is most stable, thermally very stable. Even if you heat, you have to heat it to a higher temperature. So now coming to potassium, you need to still heat more because it doesn't polarize at all. Almost zero polarization. So potassium carbonate is most stable. So in the given list, what should be the order we should follow? Potassium carbonate is most stable. Then comes calcium carbonate. Then comes magnesium carbonate, and easily polarizable, easily decomposable beryllium carbonate, because beryllium polarizes the carbonate to a great extent and spoils carbonate. You can easily heat it. So thermal stability decreases from potassium carbonate to beryllium carbonate, or increases from beryllium carbonate to potassium carbonate in the given list. Among the following, the maximum covalent character. You see, I think this is magnesium chloride. No, magnesium is given. What could be this? Sulfur chloride. SCl2. Obviously, when there are two non-metals, no need to worry. They are directly best covalent, because non-metal ions will have, because due to their small size, the ions will be still small and polarize tremendously and make the molecule very covalent. Ionic, this is covalent, ionic, somewhat, this is also ionic. Most covalent these things. Here, all are lithiums. You have to appreciate lithium separately in chemistry. You have to appreciate lithium. It is the smallest ion, lithium, even beryllium, because lithium configuration is what? 1s2, 2s1. Lithium plus configuration is what? Just 1s2, 2 electrons, that's it. Beryllium configuration 1s2, 2s2. Beryllium 2 plus configuration 1s2. See, just 2 electrons, the nucleus is much exposed. The nucleus is much exposed, polarizing power will be very high. And as you go down, other than lithium and beryllium, magnesium, calcium, strontium, barium, and here sodium, potassium, rubidium, cesium, if you go, these first two members only will have this kind of configuration. The remaining will have octets in their M plus and M plus 2 ions. So the nucleus is not that much exposed. In lithium and beryllium ions, nucleus is highly exposed. So I think lithium plus and beryllium 2 plus are regarded as one of the most powerful polarizing cations. They get easily hydrated and all, that we'll discuss in apt time. Now coming to that, lithium is common in everybody. So lithium polarizes to a very great extent, but anion wise you have fluoride, chloride, bromide and iodide. So iodide being most polarizable anion, so lithium iodide will be most covalent, and that is soluble even in pyridine and benzene. To that extent it is covalent. Peculiarly, that is soluble even in water. As I told you, solubility is the most complicated phenomenon in chemistry. You need many reasons why something is soluble, why something is soluble at low temperature, something is soluble at high temperature, all these things. So dear students, will enjoy some more beautiful logics and concepts like this in one more class before we enter into a clear understanding about covalent bonding through wave mechanical model, valence bond theory. Then we'll go for hybridization theory, their overlapping of atomic orbitals, all those things will give better reasons for how covalent bonding occurs with shapes of polyatomic molecules, many interesting cases in future. Thank you very much. Have a good day. We'll meet in our next session. Thank you.